For centuries, humanity has gazed at the stars and wondered, are we alone? The vastness of the universe hints at the possibility of other worlds, planets orbiting distant suns. These planets existing beyond our solar system are known as exoplanets. The search for exoplanets is a profound endeavor. It is a quest to understand the diversity of planetary systems and to ultimately answer the age-old question, does life exist elsewhere in the universe? The discovery of the first exoplanet in 1992 revolutionized our view of the cosmos. No longer were planets thought to be a rarity. Instead, we began to realize that our galaxy, the Milky Way, could be teeming with planetary systems. This realization has fueled an explosion of research in the field of exoplanet science. Astronomers have developed ingenious methods to detect these distant worlds, revealing a staggering array of planets with diverse sizes, compositions, and orbits. The study of exoplanets offers a window into the formation and evolution of planetary systems, including our own. By analyzing the atmospheres of exoplanets, we can glean insights into their composition and potential for harboring life. Moreover, the search for exoplanets pushes the boundaries of our technological capabilities, driving innovation in telescope design and data analysis techniques. The quest to find and characterize exoplanets is a testament to human curiosity and our innate desire to explore the unknown. It is a journey of discovery that has the potential to reshape our understanding of our place in the universe. As we continue to peer deeper into the cosmos, we embark on a thrilling adventure with implications that extend far beyond the realm of science. Imagine a tiny flea passing in front of a car headlight. That, in essence, is the principle behind the transit method, one of the most successful techniques for detecting exoplanets. This method relies on the subtle dimming of a star's light as an orbiting planet passes in front of it, an event known as a transit. When a planet transits its host star from our perspective on Earth, it blocks a minuscule fraction of the star's light. This dip in brightness, although incredibly small, can be detected by sensitive telescopes. The Kepler Space Telescope, launched in 2009, played a pivotal role in revolutionizing exoplanet discovery using the transit method. Kepler continuously monitored the brightness of over 150,000 stars, identifying thousands of exoplanet candidates. The transit method provides valuable information about an exoplanet's size. The larger the planet, the more starlight it blocks during a transit, resulting in a more pronounced dip in the star's brightness. By analyzing the depth and duration of the transit, astronomers can estimate the planet's radius. In addition to size, the transit method can also reveal clues about an exoplanet's atmosphere. As starlight filters through the planet's atmosphere during a transit, certain wavelengths of light are absorbed by atmospheric gases. By analyzing the spectrum of light that reaches Earth, scientists can identify the presence of specific molecules in the exoplanet's atmosphere. The transit method has proven to be a powerful tool in the hunt for exoplanets, revealing a plethora of worlds orbiting distant stars. Its ability to provide insights into both the size and atmospheric composition of exoplanets makes it an invaluable asset in the search for life beyond our solar system. Just as a planet is gravitationally bound to its star, the star also feels a subtle gravitational tug from its orbiting planet. This gravitational dance between a star and its planet causes the star to wobble slightly. The radial velocity method, also known as the Doppler spectroscopy method, exploits this subtle stellar wobble to detect the presence of unseen planets. As a star moves slightly towards or away from Earth due to the gravitational influence of an orbiting planet, the starlight we receive from the star is affected by the Doppler effect. When the star moves towards us, its light waves are compressed, causing a slight blue shift in its spectrum. Conversely, when the star moves away from us, its light waves are stretched, resulting in a slight redshift. Astronomers use highly precise spectrographs to measure these minute shifts in a star's spectrum. By analyzing the pattern of blue shifts and red shifts over time, they can infer the presence of an orbiting planet. The amplitude of the star's wobble reveals the planet's mass. More massive planets exert a stronger gravitational pull on their host star, leading to a more pronounced wobble. The radial velocity method has been instrumental in discovering many of the first exoplanets, including the first exoplanet ever found around a Sun-like star in 1995. This method is particularly adept at finding massive planets orbiting close to their stars, as these planets induce the most significant stellar wobbles. However, the radial velocity method has its limitations. It is less sensitive to detecting smaller planets, especially those orbiting at greater distances from their stars. Furthermore, this method can only provide an estimate of a planet's minimum mass, as the inclination of the planet's orbit relative to our line of sight can affect the observed stellar wobble. Despite its limitations, the radial velocity method remains a valuable technique in the exoplanet hunter's toolkit, complementing other methods like the transit method and direct imaging to provide a more complete picture of the diversity of planetary systems in our galaxy. A glimpse of the unseen, capturing exoplanets with direct imaging. Imagine capturing a photograph of a firefly flitting around a distant lighthouse. That is the challenge astronomers face when attempting to directly image exoplanets. Direct imaging involves capturing the faint light directly reflected or emitted by an exoplanet, a feat that is incredibly difficult due to the overwhelming glare of the host star. To overcome this challenge, astronomers have developed sophisticated instruments and techniques. One such technique is coronagraphy, which uses a mask within a telescope to block out the light from the central star, much like how we use our hand to shield our eyes from the sun. This allows the faint light from any orbiting planets to be detected. Another technique is adaptive optics, which compensates for the blurring effects of Earth's atmosphere. Adaptive optics systems use deformable mirrors that rapidly adjust their shape to correct for atmospheric distortions, resulting in sharper images. Direct imaging is most effective at detecting large, bright planets that orbit at relatively large distances from their stars. These planets, often gas giants similar to Jupiter or Saturn, emit more heat and light, making them easier to distinguish from the glare of their host star. While direct imaging remains the most challenging method for detecting exoplanets, it offers a unique advantage. It allows astronomers to directly study the light from the planet itself. By analyzing the spectrum of this light, they can glean insights into the planet's atmospheric composition, temperature, and even the presence of clouds. As technology continues to advance, direct imaging is becoming increasingly powerful, providing us with our first glimpses of these distant worlds and offering the tantalizing prospect of one day studying the atmospheres of Earth-like planets in search of signs of life. The Goldilocks zone, searching for habitable worlds. Not all planets are created equal when it comes to the potential for life as we know it. One of the key factors in determining a planet's habitability is its distance from its host star, a concept often referred to as the Goldilocks zone. Like the porridge in the fairy tale, the temperature in this zone needs to be just right, not too hot, not too cold, for liquid water to exist on the planet's surface. Liquid water is considered essential for life as we know it, acting as a solvent for biochemical reactions and playing a vital role in transporting nutrients and regulating temperature. If a planet is too close to its star, any water present would evaporate into space. Conversely, if a planet is too far from its star, any water would freeze into ice. The location of the habitable zone varies depending on the size and temperature of the star. For cooler, fainter stars, the habitable zone is located closer in. For hotter, more massive stars, the habitable zone is located farther out. Planets within the habitable zone are not guaranteed to harbor life. Other factors, such as the presence of an atmosphere, the planet's composition, and the stability of its orbit, also play crucial roles. The search for planets within the habitable zone is a top priority for astronomers. Finding a planet that orbits within this sweet spot is a significant step towards discovering a world that could potentially support life. However, it's important to remember that the habitable zone is just one piece of the puzzle. Unveiling the secrets of life beyond Earth requires a multifaceted approach that considers a wide range of factors. The breadth of alien life. Atmospheric clues in the search for life. The search for extraterrestrial life extends beyond simply finding planets in the habitable zone. Astronomers are also keen on studying the atmospheres of exoplanets, searching for telltale chemical signatures that could hint at the presence of life, what we might call the breath of an alien world. Certain gases, if present in significant quantities in a planet's atmosphere, could indicate biological activity. Oxygen, for example, is a strong indicator of life as we know it. On Earth, oxygen is constantly replenished by photosynthetic organisms like plants and algae. Without these life forms, oxygen would quickly react with other elements and disappear from the atmosphere. Another potential biosignature gas is methane. While methane can be produced through geological processes, it can also be a byproduct of biological activity. Finding both methane and oxygen together in an exoplanet's atmosphere would be a particularly compelling sign of life, as these gases would quickly react with each other unless something was replenishing them. Other potential biosignatures include ozone, nitrous oxide, and even more complex organic molecules. Detecting these molecules in the atmospheres of exoplanets requires sophisticated telescopes and advanced data analysis techniques. As light from a star passes through an exoplanet's atmosphere, certain wavelengths are absorbed by the gases present. By analyzing the spectrum of light that reaches Earth, astronomers can identify the specific molecules present in the planet's atmosphere, much like how a prism separates white light into its constituent colors. The search for biosignatures in exoplanet atmospheres is a challenging but incredibly exciting endeavor. It offers the potential to detect the subtle fingerprints of life on distant worlds, providing clues about the nature and diversity of life in the universe. In summary, the exploration of exoplanets combines cutting-edge technology and scientific curiosity. We've delved into the fascinating methods of detection, from the transit method to radial velocity and even direct imaging. Each technique offers unique insights, painting a more detailed picture of these distant worlds. We also explored what makes a planet potentially habitable and the atmospheric clues that could signal the presence of life. The search for extraterrestrial life is a thrilling scientific endeavor. There are countless exoplanets yet to be discovered, each one holding the potential to reshape our understanding of the universe. If you found this exploration fascinating, don't forget to like and share the video. And if you want to stay updated with more exciting explorations into space and other intriguing scientific topics, subscribe to Puzzle Facts. Until next time, keep looking up.